Here's an interesting problem I wanted to work through. This is a problem that involves gravity and it also involves magnetism. It's a battle between gravitational and magnetic forces that cause a motion to be at constant uniform velocity. So in this particular problem, we have an incline. I've drawn the side view of it here. And I've drawn a top view of the incline here. The angle of the incline is theta, indicated here. And we might imagine we know this angle. On the incline, we have a rod. It has some mass, some length. We imagine we know the mass and length of the rod. And this rod is sliding down this frictionless incline. Now, if there was just gravity and the rod was on the frictionless incline, it would slide down the frictionless incline. And as it slid down the frictionless incline, there would be an acceleration of gravity. There would be a acceleration due to the gravitational force, and the rod would get faster and faster and faster. But we're told that in this case, the rod slides down the incline, but this rod is sliding at constant velocity. Why is it sliding at constant velocity? Now, if we had friction on the incline, that could be a reason it slides at constant velocity. It would be that the friction is somehow pulling, the friction is somehow balancing gravity's pull down the incline. In this particular case, it's actually a magnetic force that is balancing gravity's pull down the incline. So although gravity is pulling this rod down the incline, trying to accelerate it downwards, there's going to be a counteracting magnetic force that causes the rod to just gradually slide down the incline at a constant velocity. And we're going to figure out what this velocity is. On the sketch, I also drew the magnetic field, and here's the magnetic field lines from the side view. They're pointing downwards. Here they are in this top view at the bottom of the sketch here. So there we see the magnetic field lines heading into the whiteboard. I drew one other thing on this sketch to help us. I drew the velocity of the sliding rod. Remember, this velocity is constant. And I also drew its velocity in the perspective from the top. So when you look from above, a helicopter view, you don't see the full velocity down the incline because there's a component of that velocity that's left to right, but there's also a component that's up down. You just see the left to right component. So the velocity you see from above is v cosine theta. And so this is a sketch of our problem. And our problem is basically about, I've explained that there's going to be a magnetic force on the rod, there's going to be a gravitational force on the rod, and they're equal and opposite along the direction which the rod can slide, along this direction of the incline, parallel to the incline. So to show that balance, I first want to show what the raw gravitational and magnetic forces look like. And then I'm going to show you the balance between the components of the gravitational magnetic forces along the direction that the rod can slide, along the incline. So let's start with the gravitational force. I'll draw that. Of course, we know that the gravitational force acts straight downwards, so I'm going to draw it. I'm going to draw it in green. Here's the gravitational force straight downwards. And then I'm going to draw the magnetic force. Now, the magnetic force is a little bit trickier to see how that arises. But the point is that as the rod slides, there's a change in flux in a circuit. The circuit is made up by the rod, the rails on which the rod is riding, and this resistor here. So there's actually a circuit here that's made up by the rolling rod. And as the rod heads down the incline, the surface of this circuit gets larger and larger. The flux through this circuit gets larger and larger. There's an increasing downwards flux through the circuit. That tells us that there's going to be induction. There's going to be induced current. There's going to be induced EMF. if there's an induced current and an induced EMF, we have to ask the question, does it flow clockwise around this circuit or does it flow counterclockwise around this circuit? It's actually going to flow in a direction determined by Lenz's law. The flux is increasing into the surface here due to the external magnetic field that we're bathing the incline in. And so the Lenz's law in induction says that the induced magnetic field will try and cancel this this change in flux out. That means it will try and create a magnetic field that's out of the screen. And if the magnetic field is out of the screen, I can use one of my right-hand rules to tell me that the current flowing around the loop, that must be in a direction that is counterclockwise. And so I want to indicate that current. I'm going to indicate that in brown here, running out of colors. Here goes the current. This is the induced current. This is the induced current that makes an induced magnetic field that's out of the screen, that's counteracting the flux, changing flux by the external magnetic field into the screen. If this current is flowing this counterclockwise direction around the circuit, then it's flowing in this picture here from the bottom of the rod to the top of the rod in this top view. And so this current is flowing up the rod. Based on that, we got a current in a magnetic field, the external magnetic field. We can figure out the direction of the magnetic force on the rod. So I'm going to put the palm of my hand in the direction of the current. It's up the screen, curl my fingers into the screen. That's the direction of the magnetic field. My thumb is pointing towards the left. That's the direction of the magnetic force. Okay, so at this point, I recognize that I've got a downwards gravitational force and I've got a right to left magnetic force. The gravitational force is obvious, is due to the pull of the Earth. The magnetic force is less obvious, is due to the magnetic field, is due to the induction due to the magnetic field, the induced current due to the induction in the magnetic field. So we got these two forces. Now, one of them's horizontal, one of them's vertical, but each of them have a component that's along the direction of motion. So the component of gravity, I'm going to indicate this in green, is Fg sine theta down the incline. And the component of magnetism, the magnetic force, I'm going to indicate that again in brown, that's going to be up the incline. That's actually, by the geometry, it's Fb cosine theta. And so we've got a component of magnetism, Fb cosine theta, sorry, this is hard to read, and a component of gravity, Fg sine theta, that are up the incline and down the incline. And it's these two guys that are in balance, that counteract one another. And this is really from our picture now. This is the key mathematical starting point, that Fb cosine theta, the component of the horizontal magnetic force due to induction up the incline, is going to be balanced by the component of gravity acting down the incline, Fg sine theta. And what we're going to do is fill in for how the gravitational force works in this situation. It's actually simple. It's just mg. Fill in for how the magnetic force arises in this situation. It's more complicated. It's induction. And by filling in how these two forces are working in this situation, will arise at a relationship from which we can calculate the velocity in terms of the things that we knew in the problem. There was the angle of the incline, there was the mass of the rod, there was the length of the rod, there's the magnetic field that the arrangement is immersed in. And so as a next step, I'm going to go over here on the right and write down an expression for Fg. Let's say it's going to be straightforward. I'm going to go over here on the left, and I'm going to write down an expression for B. And as I say, that's going to be more complicated. And I'm going to then fill in those expressions for FB and FG. I'll then be able to rearrange this master equation here of the equilibrium between the forces to rewrite it as an equation for the velocity of the rod on the incline as it slides at constant velocity down the incline. So let's start with the case of gravity. In the case of gravity, this is really straightforward. Fg is just the mass of the rod times the acceleration of gravity. So we know the gravitational force if we know the mass of the rod. What about in the magnetic case, the magnetic force? Well, there's actually three equations that are put together to figure out the magnetic force over here. And I'm just going to write the three equations down, and then they'll just walk through them, and then we'll put them together. Okay, so here's my understanding of the magnetic force, how the magnetic forces arise. And it's quite a story. It's quite an interesting story, but it ultimately leads us to this equation downstairs here, this complicated equation. I'll explain it. That tells us the magnetic force in terms of the magnetic field, in terms of the length of the rod, in terms of the velocity of the moving rod, and the resistance of the resistor in the circuit. So the starting point that I used was this first equation. This is a rod carrying a current in a magnetic field. There'll be a magnetic force on the rod carrying the current in the magnetic field. That's given by this is the field equation from magnetism, given by this equation here. So this relates the magnetic force that the rod is experiencing to the current that the rod is carrying. Why does the rod carry a current? The rod carries a current because of induction, we said. And so in this second equation here, this is the Faraday's law of induction applied to a rod in motion. Faraday's law of induction for a rod in motion says that the induced EMF, that's over on the far left, is equal to BLV, where B is the velocity of the rod, L is the length of the rod, and V is the motion of the rod perpendicular to the magnetic field. Now, in this case, we have to be a little bit careful here. The motion of the rod perpendicular to the magnetic field is V cosine theta. It's not V, because some of this motion is also in the direction of the magnetic field. It's parallel to the magnetic field. So that's one little subtlety here. The other ingredient, if you look in this equation, this is an equation for the induced EMF. But really, I need the induced current to go in the field equation here. But of course, the induced EMF is related to the induced current through this resistor, through Ohm's law. And so I've also hidden a third equation in this second line. It's Ohm's law. But anyway, the first equation tells me the relationship of the force to the current. The second equation is telling me the relationship of the current to the velocity. And that's a key thing. If I put these two equations together, that is, if I plug this expression for I in terms of velocity into this expression for the magnetic force in terms of I, you get this equation down here. And this is the equation, this is going to be the partner equation for this equation for gravity. We said this one's really simple. The mechanism is simple. This one's more complicated, the mechanism more complicated. But these two equations are the ones I'm going to plug into my equilibrium of forces equation upstairs here. So if I do that, I'll plug in over here on the left-hand side that the magnetic force is B squared L squared V cosine theta over R. That's a mouthful. I'll plug in mg on the right-hand side. That's simple. And at that point, I'm going to just rearrange for the velocity v to get the velocity v on the left-hand side of the equation, and all the other stuff on the right-hand side of the equation. So let me just write that down. I'm not going to do all the algebra or rearranging it. I'm just going to write it down. And here's the answer. This is the velocity of the rod as it slides at constant velocity down the incline in terms of all the parameters of the problem. And those parameters were, let's start with the rod, the mass of the rod, the length of the rod. They were the magnetic field that the rod was immersed in, and also the gravitational field that the rod experienced. And they also involved the resistor that made the circuit in which the current was induced. So that's in the numerator here. You can see from this expression, right, that this velocity involves gravity and magnetism, because you see the gravitational and magnetic fields. It's a comparison of gravity and magnetism because you see gravity in the numerator and the magnetic field in the denominator here. This velocity will depend on the mass of the rod. So if you increase the mass, the velocity will get bigger. Gravity gets bigger and pulls the rod harder down the incline. If you decrease the mass, the velocity gets smaller. The gravitational force pulls less. So that makes some sense. If we increase the length of the rod, the velocity gets smaller. If we increase the length of the rod, we're increasing the magnetic force by increasing the induction. So it makes sense that the length of the rod sits in the denominator here. Also, if we increase the magnetic field, of course, we'll increase the magnetic force and we'll decrease the velocity. If we increase the gravitational field, if we could do that, we would increase the velocity because gravity would get more powerful. There's also over here a complicated dependence on the angle of the incline. This dependence came about because, you know, it was a component of gravity down the incline that was involved in the equilibrium. It was a component of magnetism that acted up the incline that was involved in the equilibrium. And it also arose from this V cosine theta here. It was only the left-right motion of the rod and not the up-down motion of the rod that contributes to the induction and contributes to the magnetic force. Anyway, that example is really a grand tour of magnetism, magnetic induction, and forces in equilibrium, this balance between gravity and magnetic forces.